Dámy a pánové, tady je Sara Polak. Vítejte v poslední přednášce prvního dne COFITu. Je 5 hodin a nás čeká úžasná záležitost jménem paralelní a distribuované výpočty, compute, HPC, GPU, big data, všechny tady ty buzzwordy, které jste zvyklí poslouchat paralelně s tím takovým tím sexy tématem umělé inteligence, strojové učení atd. My se dneska podíváme hodně pod kapotu tím, že vlastně se podíváme na to, jak tady ty architektury vůbec fungují. Ono je krásné mít velmi elegantní algoritmy na zpracovávání dat, ale pokud pod tím ty jednotlivé uzle dobře nefungují a pokud ta architektura není dobře nastavená, tak toho člověk holt moc nezmůže. No a koho jiného mít na vykopnutí této přednášky než pana profesora Pavla Tvrdíka. Pan profesor Tvrdík je naprostý pojem na FITu ČVUT, protože samozřejmě zakladatel, ale i vede tady tu úžasnou skupinu. Například dělal i výzkum, pane profesore, to se vás potom budu muset doptat na vlastně sledování dat z vesmíru a identifikování různých objektů, takže dělá opravdu astronomickou práci, jak metaforicky, tak doslova. A vykopne tím, že nám představí právě výzkumnou skupinu o paralelních a distribuovaných výpočtech. Potom tady máme i Jana Olšinu z Valea, Tomáše Pajurka z Datamou a potom finálně Tomáše Sedloně z Adastry. Opět to bude taková hybridní kombinace českých přednášek i anglických přednášek. Pokud jste na první přednášce dne a říkáte si, proč to sakra dělají dvojjazyčně, tak to tak děláme, protože chceme ten náš úžasný český talent dostat do světa, aby o něm všichni věděli. A nejenom tady v tom odvětví, tak jsou Češi naprostá špička a FIT v tom opravdu pedlí, jak na akademické půdě jako takové, tak právě s multioborovým propojením s průmyslem. Takže já už to za sebe uzavřu, já se osobně moc těším a tady to byla jedna z mých nejoblíbenějších přednášek loňského COFITu, tak se těším, že si tu tématiku zopákneme. A pane profesore Tvrdíku, já vás tímto vyzývám našerovat si vaši screenu, a abych použila dostatek anglicizmů v jedné větě a vykopnout to za nás, protože já už za sebe nemám co dodat a vy to umíte nejlépe. Děkuji moc a těšíme se.
Tak jo, děkuji za slovo. Pochopil jsem to tak, že mluvíme teda česky nebo anglicky?
Pokud chce, víceméně je to na vás, takže cokoliv je vám komfortnější nebo v jakém jazyce máte.
Mně jde o to, jestli očekáváme, že na druhé straně jsou teda česky nemluvící lidé.
Myslím, že jich tam možná pár bude. Myslím, že to je převážně české publikum, ale v angličtině by to bylo naprosto skvělé, protože to potom můžeme krásně odprezentovat do světa. Takže pokud je vám to v pořádku, tak v angličtině by to bylo moc fajn.
Já ty slajdy mám anglicky? Nebo
no tak to se úplně nabízí.
No. Tak já to zkusím anglicky.
Takže,
dear viewers of this meeting, my name is Pavel Tvrdík. I am head of the research group Parallel Distributed Computing at FIT. And within 10 minutes, Sarah, 10 minutes, how many minutes do I have?
10 minutes is amazing.
Yeah, okay.
Thank you.
So I'll try to somehow wrap up what we are working on and how is it related to the topic of this session. So, of course, the buzzwords are everywhere today for us. We have been working on that HPC, high performance computing, parallel computing for roughly 20 years. And we have actually a large course in master program where we teach OpenMP, MPI programming. And in my room, there are people who work on really the biggest supercomputers in the world currently. So what is HPC? We will talk about many things today, like GPU, big data, HPC, scalability. So all these buzzwords relate to big machines. And the platforms for HPC has been going through very interesting development after the year 2000, because what happened after 2000? The Moore's law turned to parallelism. As you know, Moore's law said that the number of transistors per chip increases twice every 18 months. So what happened? We have been getting multi-core CPUs from 2000 on. And currently the CPUs, which are commodity in our machines, have tens of cores. And therefore they are inherently parallel. And at the same time, the companies like NVIDIA has gone through the GPU accelerators. And we have thousands of small chips, small processors on each GPU chip. So if you look at really big machines, so we are talking about petaflops. What is prepared for next 1-2 years are exaflops machines, and these machines have millions of cores, millions. So it's something which normal people can hardly even imagine. It's something really beyond the imagination. What does it mean to have a machine which is able to execute 10 to 18 operations per second? I can't. It's something I really don't know how to put into the scale of my word here. So the HPC world is related or is concentrated along the top 500 org list, which is every year updated twice. So there is a big supercomputer conference which this list is updated, and you can find top 500 as to the performance. And the machines are really today close to exaflops. In Czech Republic, we have the biggest machine in Ostrava, you probably know, IT for Innovation. They are building a new machine now. Currently, that machine called Cílem, which is there for about 4 years, is something like 450 in the top 500 recent list. So what we are doing in our research group, we are in process of preparing so-called EXA HPC lab. This is a research lab where we hope, actually we are in the process of closing the offers from the companies, and we hope to get the machine and the hardware within this spring. So this should be a cluster which will be really built equally as the computer engines in the biggest computers in the world. So that's why we call it EXA HPC lab. So we will be able to really do experiments on the top architectures where you have a combination of GPUs and CPUs with hundreds of cores, with special fast interconnects, with special high memory CPU bandwidth, and of course, combination of GPUs and CPUs in clusters. So what we in general, what are the topics of our research? So we started actually 20 years ago with looking at the architectures of this big machine. So something like theory, graph theory related to interconnection networks. Slowly we moved to computation. So really something which is called compute HPC. We have looked at what is, for example, interesting problem for HPC is how to handle so-called sparse matrices. So sparse matrices are matrices where you have many zeros. So these matrices can be of scale of millions of rows and columns. So the size of the matrix as 2D array is really 10 to 12 or more. But fortunately, most of numbers are zeros, and there are very few non-zero numbers. And therefore, you don't store such a matrix as a 2D array. Therefore, multiplication, factorization, and all these standard computations are getting more complicated because you can't rely on 2D matrix structure. And what is especially intriguing is that if you really want to get a good performance with sparse matrices, you are in trouble. So there are some research reports which say that if you have such a big computation based on sparse matrices, the performance is in the order of %. Really. So if you have a machine which is able to provide as a peak performance 1 petaflops, for example, the sparse matrix computation will give you 1/100th of that, meaning 10, gigaflops. So the performance is really drastically less than 1. And that's something which so far no one is able to solve. Anyway, what we are trying to do, we try to find some good formats for storing these sparse matrices such that we are able to get a better performance. Of course, we can't get much more over these few percent, but every percent is, of course, important here. And of course, there are some problems with load balancing and scalability and stability of the computations. The other topic we are dealing with is modeling of atomic nuclei. So this is very interesting area because the physicists have various models how to explain the quantum law on the level of atom nuclei. And this leads to huge models, basically with infinite dimensions. And in our team, we cooperate with some people who actually are developing these models. They are from Louisiana State University, Oxford, and they try to do these tasks computationally feasible. And you know that in nature we have elements with nuclear weight of up to 100 or more. What is capable, feasible today in numerical modeling of these nuclei, that we basically are able to do good model for carbon, which has number 12. If you go more than that, the complexity of the computation grows faster than exponentially. And this is really a challenge for optimization and programming of such non-traditional, badly scalable applications. So that's very fascinating research. And as we mentioned in the discussion before, in the last 2 years, we have looked at processing of big data which are produced by huge telescopes, radio telescopes. So what's going on in last 5 or a couple of years is that the astronomers are getting more and more robots who simply generate billions of streams of data every day, every night. And there is absolutely no chance that physical human astronomer could take a look at the data and find something interesting out of this stream. So what we are trying to do is to program computers so that they can identify with small false positives those interesting objects which these robotic telescopes have caught into their CCDs or other recording devices. So we are looking at spectra and optical spectra to radio astronomy signals and all these things. And this is something which we were quite successful last year, because what we managed was that really the algorithm pointed us to really interesting astronomical objects which were never observed by human astronomers. And this is something which is probably important for the future, because the data are there. The problem is that no one is able to get through, and we need really some smart techniques how to really find out what's interesting from the astronomical, from the point of astronomy, whether the star or the galaxy has some specific feature which was not observed before. And this gives huge potential for future combination of high performance computing, big data processing, artificial intelligence, and those robotic astronomic devices which simply produce these data in huge volumes. Yeah, so this probably all for the introduction. This is the list of people who are currently in the team. So maybe one member of our team is dealing with standard sparse linear equation system solution using combination of CPU and GPU, which is actually also a very interesting topic, because GPUs in general are best suited for solving very regular and orthogonal and data parallel applications, while sparse linear equation systems are very irregular, and it's very hard to get good performance out of these combinations. So it's actually hot research topic. It's much more difficult than to use GPUs for.
Yeah, by the end of 2019, we'll have quantum computers and everything will be fine and we'll solve all this problematic. Obviously, that didn't happen. So there's a stream of fake PR going on where there's like the talk of quantum and like all these new laws replacing Moore's law. And then there's genuine research like what you're doing. And also I, for example, heard IBM thinking of replacing their current systems with some nanotubes. So I'm curious if you could, please demystify the whole like fetish of Moore's law and quantum computers, but also maybe tell us what the current biggest block is that is basically stopping us going further, and what are like the way you would hope maybe that in 5 years the research would find itself or break through this barrier.
Yeah, so actually the Moore's law is still in place. The Moore's law is related to silicon technology. And even though it's surprising because I know 20 years ago, no one would predict that with the silicon technology, we can go that deep and that far. Actually, we are running to the quantum nanoscale features. So really the tunneling of transistors is in place. So, and of course the fragility of the silicon devices due to the cosmic rays and all these nano effects are in place. But for some reason, also due to the very high redundancy, the manufacturers still manage to push the Moore's law in the original sense. So the number of transistors per chip really increases roughly. It's slowing down a little bit, but still it's still going in that direction. And because there is no easy way how to use this huge number of, actually each CPU chip today has billions of transistors, hundreds of billions of transistors, tens of billions. So it makes no sense to make one chip, so one processor. So you put a lot of chips there. And the only problem is that all the classical computers need fast delivery of data from memory to the CPUs. And that's the main problem. Because due to the technology, the gap between the CPU performance, meaning the data which the CPU needs to run fast, and the way and the speed, the bandwidth with which the memory can deliver those data, this gap is widening. And that's because the memory technology speed, the memory technology latencies do not grow that fast as the performance of the multi-core CPUs. Simply said, you have more cores on the same chip with the same memory, and those chips need more data because you have multiple, more of them. So there are currently really, 2 years ago, it was said at those top 500 discussions that we are expecting some breakthrough in this direction because this cannot go a long way because the gap is widening. Unfortunately, within that paradigm of von Neumann model, when you need CPU plus memory and those transfers of data there and back, even though we have locality principles enforced by cache memories, it's still lagging behind. And the more CPU, the faster CPU, the more is the problem with the, I would say, wasting of CPU cycle performance. And this sparse matrix problem with HPC is exactly the consequence of this fact. So unless we will go away from the technology, which is still the same in principle as it was 30 years ago, von Neumann silicon machine, we can do hardly with anything with that. So you mentioned some new models of computing paradigms, like nanotubes, this is something which probably could help in the future. I don't have access to the, the results of those research labs. It's not available publicly because in most cases also it's related to military research. But the hope is that we will be able to come up with architectures where the dependency of CPU demand for data from memory will be kind of diminished by making these systems more non-uniform in the sense that we will scatter around the chip area. By the way, the chip area is still 2D. It's not 3D structure due to the energy and heat consumption and so on. So due to the, so the way, or the idea is that we will somehow make a technology where we will kind of mix together CPU and memory elements, but then again, you are limited by the 2D problem of surface plus perimeter. So this is something which hits the physical limits of geometry. And I personally, I am quite pessimistic that we can significantly change this paradigm until we will stay with the von Neumann model. And what are the alternatives? Of course, quantum computing is one of them, but quantum computing is something completely different. And even though there is a huge progress with quantum computers, they are actually running physical quantum computers on the internet. You can log to them and compute. They are not general purpose computers. And the physical limits behind the entanglement and actually the reliability of quantum computation is even worse than in classical technology. So I believe that quantum computers will be very useful for specific applications. But actually, Professor Feynman, who actually started this thinking about quantum computing, he actually stated at the beginning, let's use quantum computers to do modeling of quantum phenomena. Of course, for these applications, they are irreplaceable. We can't do it on deterministic von Neumann machine. But vice versa, if you want to compute set of linear equations on quantum computer, it makes basically no sense. So there are some specific algorithms which are handy, and but I don't believe that they can really replace a standard machine. So what I think is what will happen in the future, that we will have still these machines and they will have various accelerators, GPU accelerators for computer graphics and data parallel applications, quantum accelerators for those applications which are kind of easy to run in this quantum model because it's non-deterministic and you can't easily make it deterministic by, as we know, in a standard model.
Thank you very much. And that actually leads me on to one last question, if you don't mind. To what extent is the logic with which we approach methods, for example, like machine learning, and the way that we construct our algorithms, to what way is it determined by the physical constraints of what sits underneath? So, for example, if we had new ways of computing available, like quantum computing, and we didn't have to deal with parallel computing in the same way, would therefore the algorithms and the logic of them be structured differently as well? Would we suddenly have the liberty to approach problems from completely different angles because we wouldn't have that rigid structure sitting underneath? And I realize that this is like kind of predicting the future, but it's just, and it's something that's always interested me, the relationship of like the logic that we consider to be like given, but actually that might derive from the physical computing that sits underneath.
Definitely, the von Neumann machine is primarily sequential. So you run a sequence of instructions, and if you look at parallel computers today, these are just bunch of sequential computers. If you look at GPU, it's just bunch of sequential processors. just running data parallel applications, so they can split the problem to independent subproblems, to work on each of them, and then somehow join the result. So still this inherently sequential principle of phenomenon machine is there, even though we make it kind of data parallel. Whereas, of course, quantum computers, they are inherently parallel because of the superposition. You know, quantum state is a superposition of all possible states, and by some magic of observation, you get one of results at the end. And the only trick of quantum computing is that you do sufficient amount of experiments until you get something you can interpret as a result. And you rely on inherent parallelism of those quantum superposition phenomena, which is completely different from standard computational model. So that's why it goes so slowly, because we really need to change the paradigm. But still, I think that we are not on the way that if we actually understand very well the quantum law, the quantum principles, we will be able to think quantively that we will solve all the problems on quantum computers. No, I don't believe so. I don't see any, you know, there were in the history, we had in 90s, the era of so-called fifth computer generation, which was inherently based on principles of logic inference. So the Japanese built machines there whose basic computational model was first order predicate logic, and the basic operation was inference. They were perfect, but only for some specific tasks. If you want to do some reasoning based on some well-described rules, you can ignore the details of algorithmic solution because the system goes through many states and finds finally out the solution as a specific state in some state space. Again, it is nothing which can be used for numerical computation. And we are numerically oriented. If you want to solve a problem, like if you want to predict weather, what can we do? We set millions of measuring devices. We measure humidities, wind speed, whatever, you know, temperatures and pressures and humidity, and we put it into equations and compute and believe that this is the way how the nature works. Of course, the nature doesn't work that way, but it's kind of approximation. And that we do this with everything, with atomic bomb, earthquakes, whatever we want to understand in the nature. But of course, it's not very handy to describe the nature in this way, but that's the only way we currently know. And if we will have sometimes understanding that everything what is happening in nature is explainable by quantum physics. Even the macroscopic phenomena, you know that cosmology and quantum physics currently are going to be kind of merged. There is some kind of merge of these two areas, even though it's microscopic. This is promising. If we will have one universal, they call it unified theory, okay, physicists. If we will really get working, which we don't, then maybe we will be able to build machines. We will naturally understand and simulate what's going on in the world we live in. But we are not there now.
Thank you very much. And it's actually nice to see that when you put away the barriers of any kind of academic competition between subjects, that everyone is basically trying to get to the same thing, solve why the world around us works the way that it does. And I think that CERN is a beautiful example where it combines machine learning and processing the huge amounts of data, understanding what happens to subatomic and subatomic particles, and actually keeping the hardware so that it's running as well. I think that's a beautiful example of where the multidisciplinarity of studying the world around us and the consequent problem solving is really beautifully demonstrated. Pavel Tvrdík, you are phenomenal as always. Please hang around for the discussion later. Okay. Thank you very much for the introduction into the topic. And now I'd like to see how all of this happens in practice. And from practice, we have Jan Olšina from Valeo. who will be discussing this problematic in relation to the automotive industry, a hugely important industry for the Czech Republic and Czech Republic's economy. Jan, take it away. Thank you so much for being with us, and thank you again, Pavel Tvrdík.
Thank you, Sarah, for introduction. Hello, everybody. So my name is Jan Olšina. I work in the Research and Development Center at Valeo in Prague in the ground truth extraction team. What that exactly means, I will go through in the presentation as well. Today, I would like to tell you something about the validation of complex assistant systems in automotive. It's not a primarily big data topic, but it's definitely touching because we are processing some quite big data. By the way, can you see my whole presentation?
Yes, thank you.
Okay, great. So firstly, let me very shortly tell you something about myself. My education is at Charles University, originally in theoretical physics. Then I studied open quantum systems in Institute of Physics at Charles University, and eventually I switched to industry, kind of changed the field. And since 2015 to 2018, I worked in at the Valeo in developing of those assistant systems. And since 2018, I work more or less on validation and ground truth extraction topics. So some motivation maybe for starting. Surely you noticed that the systems in our cars are getting more and more smart. I would say now are kind of standard to have adaptive cruise control, which is cruise control which adapts the velocity of the car according to the car in front, or lane keeping assist, which keeps the car in one lane, and just the driver needs to control the wheel to make sure that the system doesn't do anything unexpected. But there are already some systems with higher level of autonomy. Some are listed on these slides. For example, autopilot from Tesla, or the Google self-driving cars, which are now called Waymo. And maybe you noticed that Honda announced first commercially produced level 3 self-driving car, which basically means that in some limited environment, let's say of traffic jam or low speed driving, the driver doesn't need to hold the driving wheel. So what I would like to tell you today about is some very short introduction about what does it mean to validate these systems. This is one of things that we are doing in Prague. So I will be talking about these steps that you can see on this slide. First, we define some statistical model that tells us how many kilometers we need to drive, in what conditions. Then we need to build up a reference car equipped with sensors, and these sensors need to be optimally better than the sensors that we are validating. Then comes the part of data logistics, which means the processing the data, moving them around, and having some overview about the data. Then there is a data labeling. This is the main domain of our team. Basically, you have raw sensor data, and you need to equip them with some labels so that the computer can understand, and you can compare the labels with the outputs of the system. And at the end, you get some KPI report, which tells you if the system is okay, or if you need to improve it in some of its parts. So let's have a look on these parts. For the statistical model, there are two main parts. One part is how many kilometers we want to drive. There, the starting point usually is that we want, of course, the system to be at least as safe as the systems that are already present on the roads. The usual target is that it's 20 times safer. And then you can apply some redundancy assumptions, for example, or some other factors to get the number of kilometers. And the other part is the decomposition of the data into some conditions that you can control, because you want as diverse conditions as possible. So you can, for example, specify time of the day, weather conditions, type of road, and other parameters, velocity, and so on. Other thing which you can do is also specifying some diversity in regions. There is example you can see in one campaign in Japan. So obviously you don't want to drive on one highway around the main city, but you want as much diversity as possible. So you specify in these regions how much you want to drive, specify some minimum, let's say. The other part is the build-up of the reference vehicle or vehicles. What you can see here is the typical setup of a vehicle in the test track which we have in Milovice. The car is equipped by many reference sensors. For example, on the roof, what you can see here are lidars that are for mapping of lanes. They are looking back on the road to see the lane markings. There is also a lidar cocoon, which creates sort of cocoon of 360 degrees around the car. So we have complete coverage. The car also has like 4 radars. For example, here I listed only one of them, USB camera. And the typical data flow can be around like 0.5 terabyte per hour. So this is the number in which we work with. I will not comment in exact all these systems. I just wanted to show you this photo of systems on the rear of the car. You can see it's filled in with electronics and many different systems with the recording setup, which includes also like recording of data and processing and connecting of these sensors together. Now let's have a look shortly at the toolchain and data. So we need to first move the data. This is a logistical challenge on its own, because at some amount of data, it's just easier to ship the hard drives by mail than just trying to feed it through the internet, unless you have other infrastructure for that. And then we have a batch of processing jobs which are running on our own infrastructure. We are using Jenkins for that. And important part is also elastic stack technology, which is sort of interactive dashboard, which allows us to monitor the data and how we are doing with filling this objective of the statistical model. I will just show you a short video how this works, for example. So what you can see here, these graphs on the top, this is composition of weather on the kilometers that we have driven. You see the velocity graph and the total mileage driven. On the right, you see map, and we can, for example, select some region on north of Japan and see what's the mileage driven exactly there, how did the velocity distribution change, and more importantly, how did the weather distribution change, because this is what we are monitoring. Here, we can apply some selective filters. So what we will see in a short is that we can, for example, specify a particular velocity. So if we limit the velocity from 0 to 20 meters per second, so we will see how does the weather composition change, and also where exactly on the map did it happen. You can see that there is more snow, for example, and there are some particular regions where we have driven. So this is one of the tools that helps us a lot. Just go forward. The data labeling, this is also a very interesting topic. I would say this is the main domain of our team. The purpose here is that the sensors like lidars, radars, they give us some raw data, and we need to create labels on them to be able to machine process them. For example, boxes that corresponds to cars on the lidar point clouds in the middle, which you can see, and there are like labels corresponding to pedestrians, traffic signs, drivable area, and so on. And creation of this ground truth is very expensive. Like annotating of 1 minute can take to a human several hours. So what we try to do is to create some machine learning algorithms that create almost, I would say, good quality ground truth already. The output you can see on the video below, where not only it creates the boxes, but also classifies the cars into some different maneuvers, whether it's following us or cutting in or doing different maneuvers. And this is then helping the annotators to with their work, because they are then only correcting the boxes and do not have to create them from scratch. This is another example. You can see video on the left and the output of the ground truth extraction algorithm on the right, where there are road boundaries as the orange polylines and boxes that correspond to the car. So the last step then is to create some KPIs. So we have some numbers that we are tracking, and they are telling us whether we are satisfying the customer requirements on the car, whether it is safe, and whether the system needs to be improved. Because some of these systems the errors are inherently statistical. So you need for development to know this statistical information, not only one particular trace where it fails. If you are interested, this slide lists some free positions that we have open now. You can also have a look at valeojobs.cz, or after this session is over, my colleagues will be in the Valeo booth where you can ask any particular questions. And I would also like to point out that technical events, technical evenings that we are organizing currently online, but it's more like in-depth technical discussion where there is more time to really focus on some topics. So this is all from my side.
Thank you very much. You have sparked a lot of really interesting topics, and so interesting that we actually have a question from the audience, which is from Tomáš Pajurek. Thank you very much. What is your opinion on the ban of Tesla in China? Is there a fear of spying? And I guess that maybe I'll add my question to this, because, for example, speaking about archaeology, we use LiDAR to find like various structures under the canopies of trees. So we also use other technologies and other, for example, infrared methodologies to be able to find the same thing. And it depends on the context and also on the contracts that you've signed and on the money that you have available, depending on what hardware you will choose to get the data that you need. And I'm curious, when you add that problematic on top of people generally being scared of being watched, and we discussed this earlier today with the group of image processing and ImproLab, the moment that you're finding objects and especially detecting things like pedestrians, you get into like this moral, ethical realm. And especially given that I was at a very interesting talk, it was about a year ago, time goes too quickly, where they were discussing the philosophical differences between autonomous driving, for example, that's decided in Germany and that is decided in the US. That, like, yes, the methodology is the same, but the lines that you draw in the sand are different culturally. So Tesla in China is an extreme example, but what is your opinion on this problematic, like when technology ends and human nature and business starts?
Yes, exactly. So I agree that this is a very important topic, and I would not be surprised if, as you said, that the reason was exactly that China is afraid of spying, because a lot of these systems or the data we are recording are, let's say, there is a lot of data actually. And it's what is interesting, for example, if we are doing these campaigns, how to put it together with GDPR or things like that. Because in camera, there is a lot of like personal like faces of people, then license plates and so on. So what we do actually is that we are blurring the license plates or the faces of people. So even before storing them, and there is quite a high standard that, for example, we need to keep these data encrypted and only store it for some limited amount of time. So I would say that it's somewhat under control. Quite interesting topic actually is using neural network for anonymizations, because for some systems, if you provide the system with the data where the faces or the pedestrians would be blurred, so they would not work properly. So there are even like neural networks that are replacing the faces by generated faces, so that the pedestrian still looks very natural, but just doesn't correspond to a particular person.
Thank you very much. I was actually speaking with a friend of mine the other day who was saying that there are new algorithms that can actually work on encrypted data, that can be trained on encrypted data, which is crazy because in terms of like all the crazy regulation that we have here, especially in Europe, that's going to be a big technological step forward. I used to work in predictive maintenance in industry, but we used to record using sound. And basically they would ask, well, can you isolate individual voices? And you'd say, well, yes, we don't know who they belong to, but like there is a fraction of a second where, yes, you can identify a voice. And that was sometimes enough of a psychological block for the people to say, no, we're not interested. Do you have that as well? Do you come across these psychological barriers of companies saying, no, we're scared because we're not sure that this data can remain anonymous?
I would say that our customers are usually like interested if we are satisfying all the standards, like for example GDPR or other like lawful or things mandated by law, more or less. So this is the main threshold, I would say.
Fair enough. Thank you very much. And thank you, Tomáš Tran, for the question. I would like everyone watching to follow Tomáš's example and ask as many questions as you can, because you've got these unique gentlemen here, so it would be a shame to let that go to waste and not ask a question if you have one. But without further ado, I would like to move towards Datamol, one of the Prague AI ecosystem members and member companies, and Tomáš Pajurek, who will tell us a little bit more about cloud compute architecture in Microsoft Azure. Sorry, it's been a long day. We're very interested in the kind of data analysis aspect. We've discussed what happens under the hood, how data is collected, how data is encrypted. And if you could tell us more about the cloud computing architecture, that'd be great. Thank you so much, and take over now. And we can see your screen beautifully. But we can't hear you. I think you're on mute. If you could please just unmute yourself so that we don't miss anything, that would be awesome.
Hello, can you hear me now?
Yes.
Yes, sorry. The Zoom just minimized and I was not able to maximize it. So thank you very much for the introduction. Sorry for the delay. My name is Tomáš Pajurek and I work as a software architect and team lead at Datamol, where we are focusing on applying methods of artificial intelligence and machine learning to industries. We, for example, do predictive maintenance, as it already was mentioned here, and other kinds of optimizations. And today I would like to tell you something about how actually compute infrastructure in Azure works. And Microsoft Azure is actually one of the largest clouds, public clouds that are out there currently. It's the second in size after Amazon Web Services. I won't be going through what actually the cloud is, because it's a topic for itself. But for this presentation, it's enough that we imagine it as a system that allows us to basically lease any number of compute nodes and pay only for the time we are using it. We don't have to buy them. We don't have to set up them. So it's really like really hyper-converged virtualized infrastructure. And I'll be talking about how it actually can be used and how it works under the hood a little bit. So as I said, it's like really virtualized environment, meaning that you don't lease like physical machines or you don't buy them. You work really mostly with the virtual machines. Yeah? So I guess that most of the listeners are familiar, for example, with VMware or Hyper-V and such technologies. So these are the virtual machines I'll be talking about. And when you want to use it in Azure or in any other cloud, it's basically all the same concepts. You first need to choose which one you want to use. And there are multiple dimensions you need to choose from. For example, the most important one is the size. So you can choose how many CPU cores or how many gigabytes of memory you want to have on your virtual machines, and of course you need to pay for it afterwards. So typically more CPU and more RAM you have, you are paying more. But you also can choose between different types of machines. So you can, for example, choose between memory optimized and compute optimized, which can, for example, like lower your overall costs. Because if you, for example, want to host a database software, like, I don't know, Postgres, you typically want to have a much larger memory to CPU ratio. So an Azure allows you to select such a machine to have it like better optimized. You can also use some special hardware connected to the machines. For example, GPUs that were already mentioned here, or HSM, which are hardware security modules for cryptographic operations and managing cryptographic keys. Or recently, you can also start using confidential computing via the technology Intel SGX, which is like a really nice modern approach to actually do some like very security sensitive operations on computers without actually allowing anybody, including operators in the physical data center, to intercept the data being used in that computation. And you can also use more advanced concepts, for example, like spot instances, which allows you like lower the costs for the leased machines even more in some special cases. And in cases, for example, of spot instances, it means that if you have a workload that allows you to actually pause the work and resume it later, then Azure will provide you a better price for a virtual machine, but you need to count on with that the instance or the virtual machine may be shut down anytime and be moved to other physical machine or even stop completely. So it's very like much cheaper, but you need to have some other constraints on your workload, for example. So this is like a basic use case what you can do in Azure, basically leasing virtual machines with some additional advanced features. But sometimes you have some additional, for example, security requirements that you are not allowed to run your workloads in a shared physical machines. And for such cases, Azure allows you to lease basically the whole physical server or rack, where you are guaranteed to be only customer on that rack, which is of course more expensive, but you have more better security guarantees and also more predictable performance. You, for example, do not care about the noisy neighbor phenomena and stuff like that. So it's also like I would say loop back to the past, where it was like normal to actually buy or release the physical machines, but with arrival of the cloud, it moved more to the virtual machine. But now it comes back due to the various, as I said, mainly security concerns. And of course, for all machines running anywhere, it's true that you often need disks to actually write persistently some, for example, resulting data or intermediate results. And for it, you can choose between classic SSD or HDD drives that are like mounted to the network interfaces to the virtual machines. This is nice because you can basically move the virtual machine between various physical hosts or even data centers, and you can connect the same disks to it. But it's for the cost of performance, because like network connected disks are much slower than the normal one. But in Azure, you can also use modern NVMe disks that are really mounted to the physical servers where your virtual machines are running, where you really get a nice performance comparable or even surpassing the classic I would say connection of disks to the hardware. And so far I was talking about only individual virtual machines. So you can imagine it's only one operating system running on some machine and doing something. But in real applications, you typically need more of them. It's tens, hundreds, or even thousands of machines typically, let's say, serving one application or one use case. And of course, it's not possible or feasible to manage all those instances like manually. And for these use cases, Azure allows or supports them with additional features such as availability sets or scale sets that, for example, supports auto scaling, meaning that you can measure the load of your virtual machines, and Azure will automatically add or remove instances based on the load, so that there is actually optimal number of instances in some pool to handle, for example, user requests, so you don't pay for, let's say, useless machines that are doing nothing. You can really optimize the workload. And also, when using availability sets or scale sets, Azure allows you to distribute the machines between different physical racks or even data centers. So then the applications and workloads are resilient to the failures of hardware or even the whole data centers. And I will be talking about this a little bit more. But first, let me start with like brief introduction into how Azure is actually organized like globally. So it is divided into so-called geographies. There are more than 32 of them, sorry. And the geographies are defined basically by two things, by geopolitical boundaries, but also with the data residency and data privacy laws and other standards. So for example, in Europe, we have several geographies. Germany is very well known with its like strict data privacy, so they have its own geography. So this is geography, and each geography consists of one or more regions, which are like areas of some like or some physical locations where the actual data centers are co-located, and each region contains 3 or more so-called availability zones. And these zones are interconnected with some fast links, such as InfiniBand or other technologies. And Azure guarantees you that each availability zone within one region can contact the other availability zone within 2 milliseconds of latency. So it's like feasible to actually locate your virtual machines to multiple availability zones and still communicating with each other synchronously. And it gives like great resilience even for the like disasters, natural disasters that causes, for example, failure of the whole data center, which is in my opinion like amazing. It's how it's possible, how easily it's possible to achieve such a resilient system. And if I go back to the single availability zone, those zones consist of one or more data centers, but for simplicity, let's say that it's one data center, and this data center is divided to so-called fault and update domains, which basically means that the racks and servers are organized into like some logical and also physical groups. And in case of fault domains, these are physical groups where each fault domain has its own rack with like separated resources such as air conditioning or power supply. Whether the update domains is a logical grouping, and Azure like takes this grouping into account when, for example, it's updating the host operating systems or updating the hardware in the servers. So why I'm talking about this? Because in the cloud, or I would say in general in any distributed system, when you have sufficient number of nodes, you need to take the hardware failures and also update events into account, and you need to prepare your applications to handle those. But with fault and update domains, Azure guarantees you that even the fault in the whole server rack might actually not crash your whole application if you are using at least 2 fault domains and they don't crash at once. Yeah. And also, if with the update domains, Azure like can update your machines or the host operating systems without actually disrupting the applications running on those hosts or virtual machines, because each domain is updated separately and sequentially, meaning that if you have machines, for example, on this example in 2 update domains, Azure guarantees that it won't update all machines at once. It will update half and half, so you have a guarantee that your application will be running all the time, even with the updates. Of course, you need to be prepared on that, and your application needs to be like reasonably resilient and ready for shutting down and being restarted. But in general, there is no like obstacle to having your applications really running all the time without downtimes caused by planned updates or even crashes of the racks or even data centers. So,
by the way, Tomáš, I'm really sorry to be the evil policeman, but I'm just wary of time. If you could please wrap up in like 1 or 2 minutes, so we have space for questions, that'd be awesome. Thank you.
Thank you. Sure. Actually, I'm in the end already, so I just wanted to mention that I was now talking about virtual machines that are like really building stones of all modern cloud applications, but typically you don't want to use the raw machines. You want to build systems built on top of those virtual machines. And this is where, for example, systems like Kubernetes or Service Fabric or Azure Functions comes in. There are many like software architectures that allows you to like abstract the underlying machines and to actually build something that has like more business value on top of it. And Azure provides various kinds of services in this space, from really the basic application hosting through the Kubernetes or Service Fabric cluster managers, or even really serverless workloads. And also, as was already mentioned here, some HPC infrastructure for scientific computing. And in DataMall, we are mainly working at this level of abstraction. So if you're interested, check out our website. We are hiring good engineers or junior interns all the time. So don't be afraid to write us, ask us any questions. We'll be glad to talk to you. And that's all from me. Thank you.
Thank you so much. And but I'm sorry to even anyone watching, I have to be in the role of the evil person who has to keep track of the time. So I'm sorry to be boring, but this was an awesome presentation. And actually, there's so many topics that you raised there around computing and processing power and like actually putting all of this architecture together. I have a question. You might roll your eyes, but I'm just curious because keeps popping up and people keep asking me about it, which is about cryptocurrencies, especially Bitcoin, that is running on blockchain. And there have been speculations about, for example, blockchain moving onto the cloud. And there's parallel discussions like taking place around the environmental impact of like this like inefficient computing. And I was actually in a studio, we were recording something like a week ago, and I was saying it's really nice and warm here, right? Because I'm always cold. And saying, oh yeah, the people downstairs they mine Bitcoin, so like they just give us like all the hot air and it's wonderful heating. So I wanted to ask about these two things, whether in terms of like changing the way the data transfer works in society, the way that like these day-to-day things that for regular people will have a huge impact, like cryptocurrencies, whether they can be moved on the cloud, whether there is that sufficient security, and like whether the architecture is ready for it. And then the second thing about computing in general and the environmental aspect, because that's being spoken about so much. Sometimes it's fake PR of companies trying to look good, but sometimes it's a genuine concern for the trees and orangutans and everything. How those two things are synchronized, and whether research and the applied side of computing bears that in mind.
Right, so this is a complicated question, at least for me.
Oh yes, I'm sorry.
I would say that in general, the cloud is not like the best environment for mining Bitcoins or mining Bitcoins, let's say, because they are really like computationally demanding. And if you compare, if you really bought your own physical machine, I would, and using all the time for mining Bitcoin, which can really saturate your CPU all the time without actually like being afraid of that you are not utilizing it as much as you need, then it would be much more like economical to use your own hardware for it, because of course the hardware in Azure, like it's not very cheap, but it adds you a lot of additional features. For example, as I was talking about, the distribution and availability of the systems that you don't need for mining Bitcoin. So I would say it's not the best environment from the, I would say, performance point of view or economical point of view. But from the security point of view, I think it's I would say it's pretty secure. Actually, all major cloud providers, including AWS, Azure, and Google Cloud Platform, has like a lot of security certifications for running even the most sensitive workloads, such as medical systems or financial systems. So I would not be afraid of that. Yeah, but really, I would not mind Bitcoin in Azure, let's say. But regarding the other cryptocurrencies or other, let's say, blockchain technologies, it necessarily does not have to be the case, because like the more modern blockchains are not based on the proof of work, but on other proofs. So for example, proof of stake, which is not so computationally intensive. So it might be actually useful to use like a cloud for that. But on the other side, the whole blockchain is also based on the idea of distribution between of the like blockchain distribution of the blockchain to multiple parties. And I would say that the most fans of the blockchain would not be happy to actually centralize it in one cloud, for example, Microsoft or Amazon's one. So yeah, that's what I have to say to this topic.
Thank you very much. And just very quickly, the ecological side of things, is that being discussed? Is that a theme in terms of your specialization?
Yeah. So sorry, I forgot about this part of the question.
No problem. It was a big question.
Yeah. So I would divide it to two parts. So first one is how the actually cloud providers approach this topic, and I was talking about Microsoft Azure, so I will stick to that. Actually, the Microsoft Azure, at least publicly, they are like trying very hard to be carbon neutral, and they are saying they already are. They are investing a lot of money to actually research various approaches to the computing that are, like, let's say, more eco-friendly. For example, they are trying to build the underwater data center that like needs much less electrical power, because you don't have to care about cooling, basically. And the other part of the question, me personally, yeah, I would not say that I have some big contribution to the let's say eco-friendliness of the cloud, apart from making the applications more efficient and using less CPU.
I mean, in fairness, that's exactly what we need. If that happens at scale, then perfect. So, Tomáš, thank you for saving the planet. And thank you for your very insightful insight. Yes, that's a very intelligent sentence. Into cloud computing and specifically Azure. It was a really interesting way to see how the infrastructure and the architecture works. And last but not least, this beautifully brings us into the theme of big data. So we have from Adastra, we have Tomáš Sedloň. Tomáš, just please remind me, do you prefer Czech or English?
Yeah, English is fine.
English is fine, thank you. You're all so flexible today, this is great. We will wrap this up with a bow and send this abroad to the US to show them what kick-ass people we have. And Tomáš will be telling us about the pitfalls of big data development and research, and how to make data great again. I couldn't say it better myself. Take it away.
All right, hello everyone. I'd like to tell you a bit about what all kinds of stuff you can meet while developing big data. I'm a big data developer in Adastra for about 3 years. Maybe a few words about the company. We're a technology consultancy company. There's about 1,000 of us, and there's about 30 of us in the big data team that I will be talking about. There's various kinds of jobs that we do, and the big data developer needs to know a bit about everything. Most of the big data developers or big data engineers usually come from a relational SQL environment, so it's very SQL oriented. But they need to know some programming as well, and that might be a problem at sometimes. The most prominent languages in big data are Scala and Python. They are usually used for different use cases, but what they have in common is that they can access the Spark framework, which is the most common framework or the completely dominant framework for big data manipulation right now. Python is great for short POCs, and there's some great libraries for machine learning and visualization, etc. But we usually don't prefer to work with it in production environment, because It's really fast and agile if you're doing some short POC, but once you deploy it production, you then live in constant fear of whether it will fail or not. So that's not that nice. On the other hand, Scala is a static language. It's compiled, so it's much easier to do production work in there. You can test it in a much better way. And since you can use pretty much anything and everything that was already written in Java, it's very nice and easy to write in as well. And the nice thing about Scala is also that it's scalable. It's scalable from the beginning. It was developed with the scalability in mind. So everything from the parallel collections to much more complex stuff can be done in scale there. So it's great for big data. Another technology that is pretty important is Linux, because pretty much every big data platform runs or some Linux distribution. So that's great to know. And there are some specific big data technologies that you should know. The most common ones of them are Kafka for transferring data, Impala and Hive, and some NoSQL databases like Cassandra or HBase or MongoDB, let's say. All right. Some typical use cases that we do is usually offloading data between some relational databases and Hadoop, which means building some kinds of high throughput ETL pipelines. We often do a near real-time or real-time data streaming and some processing on top of that. Machine learning projects are quite common as well, and some projects with neural networks. However, in here, we are usually quite constrained by our clients or the client's use cases, because let's say if you take a model bank, a bank would like to automate its processes as much as possible to save some money. And for example, if you take mortgages, and somebody comes to a bank and says, "Hey, I'd like a mortgage," that the bank would like to be able to automate that, and let's say have some neural network for that. But it's not possible for legal reasons, because you need to be able to explain to the person who asked for the mortgage, why did you deny or approve the mortgage? So it's completely fine to use some simple model like linear regression or whatever, and to say, hey, we've denied your application because you've missed this parameter, or this parameter number was too low. That's fine. But what you can't do is say, hey, yeah, a neural network took a look at your application and they didn't like it. We don't know why, but they didn't like it. So you can't do this. So you might be a bit constrained in this on the data science projects. We also build a lot of big data platforms and administer them, and a whole separate area is IoT, on which we have another lecture altogether. So some of the interesting areas. First of them is functional programming, because you pretty much all the time need to have big data applications that are able to run in parallel instead of single thread, because if you write a single for cycle, you get locked in a single thread and all your performance is gone. We can often see this in some customers, especially with data scientists, when they've got a nice large big data platform with some heavy computational options. But what they do, they just load some data from the big data cluster, collect it to a single driver, to a single node, and then try to iterate over there or do something in pandas over there. And it does not perform very well, and then they are angry about the big data technologies. So that's not the way to do it, and you need to think pretty much from the beginning about how you're going to build your application and how it will scale and how it will run in parallel. A good thing to do that is functional programming, which requires a kind of a different thinking, where you need to do parallel operations. And you try to write small, clear functions without any side effects. So basically functions that are purely determined by what you put in them. That's the simple determination of what goes out. And once you've got this, you are able to write immutable values and immutable code, where you don't have any changing variables, but simply you transform one value to another. So that's a much better way, because once you've got this, you can scale it easily. And This is also the difference between OOP and functional programming in the mindset, because OOP says that it's reasonable to put data and the functions and the behavior together into some kinds of containers like classes. On the other hand, functional programmers say that that's not a good idea. There are some nice articles about that. For example, OOP, a $1 trillion disaster. I wholeheartedly recommend everybody to read that if you want to be serious about programming. And the functional programming says that functions and data should be independent. So basically, we have some small clean functions, and we then chain them and put the data through that as a single pipeline. And it's nice. It's much simpler. It's much easier to understand than some OOP craziness, and it's much easier to test as well. The only downside is that you need a language for that. For example, if you would take a look at some older Java, writing even a simple word count example in Spark would be stuff of nightmares. On the other hand, if you take Scala and Spark in there, you can see that like reading a document on HDFS and then doing a flat map over that, so splitting the lines into simple words and then converting the words into tuples of word and one, and then reducing them by the word to get the word count is a real simple application and pretty much the hello world application in Spark. So Scala and Python are great for this because they can call Spark. Another very common problem is distributed parallel processing, and that is if we are talking about exactly once delivery or at least once delivery, and of course guaranteed order of messages, as we can see in this hilarious tweet. So that's a common problem. The usual solution is that you have an at least once delivery, where you can guarantee that you get the message at least once, but you can't guarantee that you get it exactly once. So you need to write an application that's okay with the idea that it will get the same resource or the same message multiple times, that there will be some duplicates. You can usually solve that through idempotent operations that do not care if they are repeated and the result is always the same. So that's one of the possible solutions. Another one, for example, if you have Kafka as your streaming pipeline, this technology usually stores the data for some set amount of time, let's say for 7 days. And after this time period, you can be pretty sure that you won't get your duplicates again. So you can run some duplication on the target database after this time period, and only then use the data as without applications. That's another possible way. The new versions of Kafka can do exactly once delivery, but it leads to some unreasonable lowering of throughput. So we usually don't do that. One of the other problems that's linked to this is that the big data platforms are pretty new or immature technology. So it can often fail, and you need to take into consideration that the nodes or workers in your cluster can fail, and it does not have to be stable, or you do not have to have enough memory. So usually when one of your operations fail, you should not mark it or handle it as a failure or as an exception, but you should try again and try it a few times before you really declare, hey, yeah, this was a failure. All right. Another interesting topic is the data consistency versus high availability, because these two pretty much go against each other. So we need to weigh how much we want to be sure that those are the right data, this is the source of truth, versus how fast we want those data to be available, and if we are fine with only eventual consistency. Because the data are usually replicated on nodes in our cluster, and we need to decide like from how many nodes we need the confirmation, because we say, yeah, those data are all right. One of the nice examples of this behavior is Cassandra, which is a great NoSQL database, which can be extremely efficient and extremely fast, but it requires the normalized data, and it requires first defining your queries and then building the tables so they would fit those queries. And it has several strategies how to handle this data consistency versus high availability problem. First of them is a very simple one. It's called one, which means that we only write and read from a single node in the cluster, or a single node needs to confirm the operation, which is extremely fast, but very dangerous because we need to define that we really can read some out-of-date data. A completely different strategy is all, which is pretty sure but very slow because we now require each and every single one of our nodes to confirm the operation. So it's not as fast, and it's also dangerous in the way that if even only one of our nodes fail, the cluster is gone and we can't do anything because we require confirmation from all of them. A very nice strategy that works best is called quorum in Cassandra, which allows us, or which says that, hey, most of the nodes, so let's say 3 out of 5, need to confirm those operations, which is great because we are sure that we have the up-to-date data and we do not need as many confirmations. Because let's say that we got like 5 nodes and we write to 3 of them, and then if we read from 3 random nodes, so even in the worst case scenario, when 2 of those nodes have out-of-date data, we in every single case get at least once that's got up-to-date data. It then updates the other nodes, and we've got our answer as what's the current data, even with confirmations from only 3 nodes. So that's a good example of a great solution of this problem.
Thank you, Tomáš. And sorry, I have to be evil again. If you could wrap it up in a couple of minutes, that would be epic. Thank you.
Oh, all right, sure. That's a shame, but sure. Another usual problem is real-time processing, because usually our customers say, hey, we need real-time processing, but you need to really ask yourselves, in what kind of environment are you? If it's an old school bank, they might be used to getting their data via daily batches overnight. So even like 5 min micro batches might be a completely very few word for them. So it does not really need to be streaming at all. The usual frameworks for streaming is a Spark structured streaming. It's lingua franca pretty much in big data, and you usually need to decide between Lambda and Kappa architectures, but we don't have time for that. Another curious problems is dependency management or the cluster, because it's usually dependency hell in Java and Scala alone. But when you need to make sure that every single library on every single node in the cluster has the same version, that's another kind of hell entirely. And then a few words about some nice NoSQL databases like Cassandra, HBase, MongoDB. You usually don't have classic relational tables in here, but you've got key value stores, and it usually provides you with having extremely fast reads, and in some case even fast writes, for the price of much harder queries. For example, Cassandra can only select via primary or partition keys with great performance, so it needs fully normalized tables. So it's great if you can do that. And for example, HBase is a super fast but very, very simple, very, very stupid key value store. So it has its uses as well. And I guess there are some jokes about machine learning, and that might be it. The technologies are pretty hard to use. So usually people are quite happy with the fact that it's working, but the code might not be that readable. All right. And yeah, if you'd like to take a look at big data technologies, we are always hiring. You can grow extremely fast in Arastra. Like, I'm there for 3 years. I didn't know anything about big data technologies when I got there. I couldn't even program at all. I could just write some statistics or machine learning nowadays in R, but that was it. So there's a lot of opportunities in there and lots of projects that you can cycle through and learn interesting stuff. And I guess that's it from me. Happy to answer any questions if there are any.
Thank you so much. I definitely have one. And again, sorry for being the evil policeman, but unfortunately it has to be done. I love your use of memes. Memes are actually very interesting anyway, because it's a viral spread of symbolic information, which I find anthropologically fascinating. But you beautifully demystified machine learning. That is basically glorified statistics, and that's beautifully put. I would like to go back to the start of your presentation when you mentioned the bank situation, for example, and you said that people often don't understand, and they talk about like autonomous decision making, and it's often where they find the natural aversion towards AI, that they think that some evil robot decided that they cannot have their loan. We don't have artificial general intelligence. Like, there are not like robots making emotive choices. It's either a badly programmed algorithm, or like you've got shitty data and the algorithm made the right choice, which is like why the algorithm was introduced in the first place. So the transparency of algorithms, what do you think could be done better so that they're not seen as such a black box by the public, but also by individual customers?
Yeah, I honestly don't think that there's much to be done. I'm not like a data scientist, so I don't have a deep understanding of the topic, but I'm afraid that there's not much to be done, because if you've got a data science fellow with a PhD in data science, and he really writes some kind of really convoluted model, not many people are able to understand it, and that's a problem with general population, as you've mentioned. But it's also a problem with his colleagues, let's say in development or in DevOps, because somebody needs to take that crazy model in Python and then apply it at scale, or to be able to use it in production, and that's usually pretty hard as well. So yeah, like AI is a threat, and I don't think there's anything we can do about it.
But maybe a threat not in the form of killer robots, just bad popularization. I would really like to, this was our talk that ends the first day of COFIT, which was on the topic of computing, HPC, GPU, and big data. We have had Professor Pavel Tvrdík, who leads the parallel and distributed computing group, research group here at FIT. We had Jan Olšina from Valeo, who was talking about autonomous driving, as well as the different methodologies that we can find in this particular very sexy area of automobile industry. We had Tomáš Pajurek from Datamol, who was telling us a little bit about Microsoft Azure, and we also had Tomáš Pajurek from Adastra, who was telling us about big data and the difficulties connected with that. I think for me, as last year, I'm fascinated by this topic, and I think that it's beautiful that we can get the cooperation of the hard metal, but also the data that sits on top of that, and then the analysis that sits on top of that data. And I think that particularly machine learning operations is going to be a field that's going to go through a big revolution in the coming years. It's something that we've discussed once with Pavel Tvrdík, that, yeah, it's great to have the algorithms, it's great to have like the bits of metal, but then someone needs to put it all together. So I'm really excited about this multidisciplinary side of things. Gentlemen, thank you so much for being here with us today. Thank you for all the work that you do. If you as students have any questions, please remember that you can message us. You can ask all these gentlemen anything. We have the virtual hangout space where you can come and ask your questions. And there's also a Clubhouse discussion today at 8:15, which is open to everyone and free for everyone to discuss their thoughts and dreams and feelings on not just parallel and distributed computing, but anything else related to technology that's being taught at the Faculty of Information Technology. Thank you so much. It's been a great honor. Have a lovely evening, and I will be looking forward to our Clubhouse discussion. And tomorrow we start day 2 with something very exciting, and that is embedded security. Encryption, access management, delegated authentication, and all these beautiful things. So come and join us tomorrow, 10 o'clock, for the second day of COFIT. Thank you very much, and have a nice evening.
Thank you.